Hello, everybody. This is 5.2. It's logarithmic functions. And in 5.1, we did exponential functions. And these kind of serve as a review, really, from algebra. So we saw the form of exponential function being that b power x, right? And the base has to be positive, and x is the exponent. So here for the exponential equation of the form b power y equal x, where b is positive and not 1, we can transition to the logarithmic definition with connecting it with the exponential form. So here you have y equal log x with base b, so the base is b here, if and only if x equals to b power y. So look at it this way, so it's easy to remember. You have this form here, if and only if x, look at this here, this base is going to stay the base, right? So b, maybe we should do it this way. If and only if, start with the base b power y equal this inside here x. So a simple example to think about is 2 power 3 is 8, right? So if you want to reverse it, it's going to be this way. 2 is the base, so that's the base. And you need the exponent, so this log is equals to this exponent value, such that 8 is here, right? So this is a nice example to remember it and to figure it out. And we can do some examples. So solve each of, so let's do some examples. And this is given in a form of logarithmic equation. So solve this equation. What is x such that it is this way, right? So 3 power 4 equals to x. 3 power 4 equals to x, that's 81. So that means that log of base 3 of 81 is 4. And similarly, now you see 16 power x is going to be equal to 4. X power 3 is going to be equal to 8. So 16 power 4 power x equal to 4. And we can, you see the 16 is 4 squared, and that gives us x as being 1/2, right? Because 16 power 1/2, which is the square root of 16, is 4. So that was the question, 16 to x. So what is, just like we will solve this equation here, because 16 and 16 are the same. So same thing here, you're going to do that for x, this one, x to the third equals to 8, right? And that's similar to the example I did. Okay. So the two widely used systems of logarithmics are common logs and natural log. So here a common log versus natural log. The common log is base 10, and on a calculator you see just log there. The natural log is ln on a calculator, and it is the log with base e, right? So these two are the two known ones. And keep a note that these you have these two on a calculator, and you don't have any other logs on a calculator, and you will need to switch if you want to calculate a different base. And let's see some laws of logarithmics first. Just like exponents, we saw, but this is done, of course, in the reverse, because the inverse function for exponential is the log. If you can move from a single log, if you have a product, to two logs or expansion here, using addition. So a simple way, let's say 2 times 3, you can change it to 2 plus, this is just a simple trivial example to show, right? But we need these properties to simplify or solve equations. So same thing for division, or if you have a quotient. Remember, for exponents, if you have a division, you subtract. So here you're going to subtract the two log terms, right? For exponents, if you have two exponents, you multiply. So here, a similar thing. You have log of this m power n. So what happens is this m comes to the front, right? So that's how you would simplify that. Logarithmic value of 1 is 0, and logarithmic of b, while the base is b, is 1. And we're going to see this when we do a change of base formula, because if you have some type of base that's not 10 or e, then because here the common log, if I didn't mention it, it's of course here 10. The common log is base 10 and the other one is base e. So that's going to be, there is a formula that says change of base, where you're going to figure out this by doing the log of b over log of b, which is 1. So anytime this inside here is same as the base, you're going to have 1, and it's a nice property to know. And if you want, maybe we'll mention it later if it's not here. But the change of base, let's write it here. If I have log of b and this is a, you do log of b over log of a. And you can also use the natural log. Either way will work the same way. You can use the common log or the, so this is the top and this is the bottom. That's for the change of base formula. So I have this multiplication. It can switch into this addition of the two logs. Then I have the exponents, which can be switched to the exponent coming to the front. So log 1 and log 3. And this is the simplified form, right? So this is kind of expand, and you need to know both ways. So for the next one, similar thing, we have a divide, and divide what? This, which means that, you see it, minus this part here, because division minus the second one using log 2. Then this is an exponent. It's going to come here using log 3. And that's it. So this is usually put a note not to confuse this. So this is not a product. So don't do like log of 2 x squared times log of 1. No, not a product. So you can't expand that. And this is the final thing. If you have radicals, of course, you need to switch them to their rational exponent, this 1/2. And that's going to give you now a product here, and it's going to give you a division, which is a subtraction here. So that's where the product comes, and this is where the subtraction comes. And after that, we go ahead, take care of the exponents to come to the front. And log ln e, that's two inverse functions, so they're going to cancel each other and they equal to 1. And you can also try it on a calculator, do on a calculator this, and it's going to give you 1. And that's it. So that's a most simplified form for this. So you don't leave the exponents. So for what about the graphs? Once we understand these properties, we understand what we can do, and understand also that log is a inverse of exponential functions. So there are going to be some things that reverse. So remember, for exponential, the domain is all real numbers. So here the range is all real numbers, because the exponential function and logarithmic functions are inverse of each other. And so the domain of this one, of the exponential function, this is the range of exponential function. And for this one, this log, it's going this way. So this is the domain of log. This is the range of log, right? And you see they're the same. So the domain of this exponential function is going to be the range of this logarithmic function. And here, the range of this exponential function is going to be the domain of this logarithmic function. So its domain is 0 to infinity. So there is in that one we had horizontal asymptotes. In this one we're going to have a vertical. Its graph passes through 1, 0. Remember the other one, 0, 1. It is continuous and it's over its domain. So if we take that function that we did, the ex, and you reverse it, since they are inverse of each other's, anytime you have functions inverse of each other, they're going to reflect with this line. So if you take this point, 0, 1, here it's going to be 1, 0. And same, any points you have here, you're going to reflect them, and they're going to be here. So this horizontal asymptote here, it's going to become a vertical asymptote here for this natural log function. All right, so other properties, the inverse one, I spoke about it when it came to solving. If you combine the natural log with e, and now if you the two ways, you're gonna get x. So if x is 1, you're gonna get 1. If x is just x, you're gonna get x. We did use this one, so you can also use this one. Here, when you combine these two, they cancel each other. So let's look at the example. Solve this type of equation. You have, let's get e by itself. We divide by 2, we get 2.5. And remember, this is not type 1, not type 2. This is 3, which means you need to take a log to both sides. And if you have e, you take a natural log to both sides, and that's going to cancel this part here. And you get x plus 2 equal. And so remember, this is what we call the exact solution. This is exact solution. So if you're asked for exact solution, this is it. If you're asked for some type of approximation, then you use a calculator and you round to whatever you need to round to. So let's use logarithms to solve the equation, or use the properties, whichever are needed here to solve for t. So to get t by itself, we need first to get this e by itself. So we divide by 7. Then we're going to take ln to both sides, and that's going to give us, and this is going to cancel, and we get ln of 1 is 0 and t equal to. And you can check whether that's correct or not. So use logarithmic to solve this equation. We have, of course, t is here at this bottom, and we can think about different ways. How would we solve this one? So maybe we want to cross multiply. If you cross multiply, you get t equal 200. And of course, here, instead distributing, you can distribute, or you can just get rid of 100 by, so because you know you're interested in having this, so the less the better. And we can subtract 1. You get 1, and we can divide by 4. And we take and that's going to give this. And now we divide by ln 1/4 by negative 0.6. Again, this is an exact value to it. And if we need the approximated value, so we're going to do all right, so two decimal places. So try it, and you should get 2.31. All right, so we need this by itself. And these are clear steps, you know, until here. Then you take ln to both sides. And you simplify. So let's look at this application, then we close. Of course, now you're familiar with this type of problems we have been doing for a while. You know that t stands is between 1 and 6 for this model, but the 1 actually stands for 1907 and the 6 for 2007. So we've done this a few times now, and you start getting used to them. W is measured in years, and T is measured in 20-year intervals, right? And this is about the average lifespan of American women, and based on whatever studies they did. So here, of course, it's just what we have done is, if you're asked for 1907, we're not going to substitute 1907, but here it stands for 1, right? So for 49.9. The only difference in this example is now you have ln, and you evaluate whatever that is, and you know, but in this case it's 1, and you, which is 0, ln of 0, ln of 1 is 0, and you get 49.9 years. And here you also got a hint, but if you don't get a hint, you need to figure out based on the 20 interval, what does the 2047 mean? It means 8, right? And you substitute the equation and you figure out what that is as far as the calculator should get. Maybe it is 7.5 here. All right, so a quick review. And if you're not familiar with these, maybe to look into some other videos, because these are kind of algebra, and now they're coming into this course as a foundation to understand the behavior of exponential and logarithmic functions, and of course their equations and their properties.